Welcome to the Walton Pi. Today I'm going to go through the following two problems that have to do with power series and convergence related to complex analysis. If these are videos that are helpful, please consider liking and subscribing. It really helps me to keep making these types of videos. So let's get started. So let's suppose that we have a power series, so it's the sum of an times z to the n, which converges at some z0 not equal to the origin. We are going to prove that it must converge in the disk d sub r of 0, so the open disk of radius r centered at 0, for a radius that is equal to the modulus of z0. So the way we're going to be doing this is we know that every power series has some radius of convergence. So that means there is some r, so that the sum of an z to the n, this converges absolutely if modulus of z is less than r, and it's going to diverge if the modulus of z is greater than r. Now the question becomes, how does this help us? Well, we know for a fact that it converges at z0, so it converges at some z0. Now, we don't know what happens on at the point where it's equal to the radius of convergence, but we do know that because it converges at z0, that means we know for a fact that the modulus of z0 has to be greater or less than or equal to r. Because if it was bigger than r, then it would have to diverge because of this condition here. So that means that we know that the modulus of z0 is less than or equal to r, and we are only looking at the points inside the disk of radius r, which is equal to z0. So we are looking at the points where the modulus of z is strictly less than the modulus of z0, which is less than or equal to r, which means it has to converge. Therefore, it must converge everywhere in the disk of radius r. Okay, does that make sense? I hope so. Now let's look at the next part. The next part is actually going to use this first part to be able to help us out with this problem. So we are going to have a function h that is a function only of a real variable. And we know that h of x is equal to the sum of an x to the n, where it's going to converge everywhere for all x in that different region. We are now going to prove that h is the restriction to the real axis of some holomorphic function in a neighborhood of the origin. So we are going to say that our function f of x is defined to be the sum from n equals 0 to infinity of an z to the n, where this an is the same an that's in h. So that means that here h of x is just h f of z, not x. So that means that h of x is just f of x, where we just say that x has to be a real number. So now what we're going to be doing is we are going to be looking at, first, we clearly have h as a restriction to the real axis of a function. The question is, can we show that this is holomorphic? Well, if we can show that it's analytic implies that it's holomorphic, and analytic just means, oh, look at that, it has a power series representation. Now the question is, does it converge? Because that's the only other thing. Analytic means it converges at that point. We just have to show that this converges. So let's go and show that it converges. Well, what does part A say? Part A says that if we know it converges at some z0, then it's going to converge in a disk inside that region. So if we were to look at our complex plane, it's converging on this region right here. It's going to converge on this region from negative r to r. So we just pick one of these values. So here's our point z0. That means that we have on the disk of radius z0, or modulus of z0, everywhere in that disk is going to have to converge. That's from part A. This is a neighborhood of the origin. So what we have is we know that f of z converges inside a neighborhood of the origin. And we're done. That is the entire logic that we would have. So to write down your proof, you'd have to formalize this and write it down a little bit nicer. But that's the idea. That's the idea of how this is going to be shown. I hope this video was helpful in understanding this concept. If it was, please like and subscribe. Check out some of my other videos. I hope you have a great rest of your day, and hopefully, if you get stuck, you'll come back here. So, have a great rest of your day, and good luck with all of your math.